Hello everyone and welcome to our CommScope beamforming antennas for 5G NR webinar, the second one in this Connect webinar series. My name is Vivian Chia and I'm from the APAC marketing team from the service provider business. Before I hand it over to our speaker, I would like to highlight some housekeeping matters. Please note that Google Chrome offers the best webinar experience. So if you're not using Google Chrome and you encounter any issue, we would suggest that you log out, switch to Chrome, then log in again. Live simultaneous interpretation in Japanese is available via a widget called Live Japanese Interpretation, shown by the orange arrow below. To listen to this webinar in Japanese, first, mute the media player. Second, select Japanese using the drop-down list. Third, click Connect and you are all set. If you cannot find the widget for some reasons, click on the icon at the bottom marked by the letter A. The instructions to connect to the live Japanese interpretation widget is also available as a PDF in the resource list as shown. Please give us your feedback at the end of the session. You can access the feedback forms in the resource list widget located at the bottom left-hand corner as highlighted. The forms are available in both English and Japanese, and you can just pick one to give your feedback. Each respondent will receive a token of appreciation from us. Please also note that we will do Q&A only at the end of the session. But meanwhile, if you have any questions, you can submit it using the Q&A widget at the bottom right-hand corner of the screen. All the widgets you see on the screen are adjustable in size. You just need to move your cursor to the bottom and the right edges, then drag accordingly. If you would like to maximize the media player, just click the square on the top right-hand corner. Please note that a PDF version of the slides will be shared post-webinar. With that, I would like to hand it over to our speaker for today. He is Dr. Muhammad Nader, Director of Mobility Network Engineering. His bio was shared earlier and is also available in the bio widget. So I won't go through it again so we can actually leave more time for his presentation. Over to you, Dr. Muhammad.
Thanks, Vivian, and a very warm welcome to everyone joining our talk today, Beamforming Antennas for 5G New Radios, or in lighter terms, Rise of the Beamformers. I'm Mohammed Nader, the Director of Mobility Network Engineering at CommScope, based in Melbourne, Australia. Today, we will be touching on a new generation of 5G antennas technology, the so-called beamformers, and how to choose the optimal configuration for a successful rollout strategy. Here is a more detailed view of today's agenda. We will start by discussing the need for beamformers and then explain their configurations and modes of operation. Five G has seen very good global adoption so far. According to the GSMA Global 5G Landscape Report as of July 2020, 87 operators in 39 countries have already launched one or more standard 5G services. These nations can be seen highlighted on the map. Many other nations around the globe are also undergoing 5G field trials and investments. By 2025, the GSMA predicts around 1.7 billion 5G connections, covering more than one-third of the world's population. As we all know, 5G has tough KPIs to meet, including astronomical data rates, connection densities, and latencies, among others, as can be seen from this chart. However, spectral and spectral efficiency are key factors in meeting such stringent performance targets. No wonder that spectrum is always the most valuable resource to operators. Speaking on spectrum, the industry has been very proactive in sourcing the needed additional spectrum resources. mainly through the ITU's World Radio Conference, which is typically held every 3 to 4 years. To give you a better idea, it is estimated that around 17 gigahertz of additional bandwidth has been identified as mobile broadbands in the most recent ITU World Radio Conference, WRC19, held in Sharm el-Sheikh, Egypt, last November 2019. So how do you think we can meet the 5G capacity needs with spectrum? Well, there are like two main roads to take, but both lead to adopting beamforming techniques. The first road is about acquiring more spectrum, while the second is about improving the spectral efficiency. As for acquiring more spectrum road, we are targeting around 100 MHz of bandwidth per operator. Such generous allocations are not available in our current sub-gigahertz bands. This forces us moving into higher bands. But as we go higher in the frequency range, as the signal fades faster, creating coverage gaps. The beamforming antennas can bridge this gap by introducing much higher antenna gains. As for improving the spectral efficiency path, that is like squeezing more bits per second into each megahertz of available spectrum, we can achieve that by activating efficient beamforming techniques such as massive MIMO and multi-user MIMO, creating very sharp beams that do not interfere with nearby users' devices, which is again another beamforming technique. Our new generation of beamforming antennas have very special skills. If you are a movie fan like me, the legendary Transformer heroes are known to transform their shapes from cars to robots, among other shapes. Similarly, our beamforming heroes can also dynamically transform their radiating pattern shapes in their fights against network interferences. And for this reason, many like to call them the beamformers. Beamformers can improve both of our link budgets and spectral efficiencies. Beamformers come in different configurations and capabilities. Each is best suited for a certain environment. They might look very dissimilar from the outside to the untrained eye. However, under the hood, they can be distinguished by three main design philosophies: built over either active or passive array structures, use digital, analog, or hybrid beamforming, and equipped with several radio transceivers starting from 88R and higher. Most cellular antennas have their radiating elements placed in arrays, similar to the example shown on the left photo. The antenna element spacing plays an important role in determining the pattern's shape and gain. For example, increasing the spacing for a 4-element array from half lambda to 2 lambda reduces the vertical half-power beam width. Even though this increases the main lobe gain, it also generates more grating lobes or side lobes, which disperse the radiated power away from the main lobe's direction, as can be seen from this pattern plot. The overall directivity, which is the antenna gain before internal losses, is a function of the number of elements n per each array and is expressed in literature as 10 log n. If we neglect the losses as an approximation, we can easily show that the array's gain is 3 log to the base 2 of n. That is, or simply put, doubling the n doubles the gain by 3 decibels. As these arrays are passive, such gain increase is attainable by shaping the beam into narrower width, similar to the element spacing concept of the previous slide. It is also worth noting that in some designs, like the one shown here, a linear array might be composed of smaller subarrays. Each subarray gets connected to a different radio transceiver. The resulting panel gain is a summation of all. However, most beamformers rely on phase shifting techniques to direct their beams. The figure here is an example of a single radio transmitter's RF path, which is being split among a number of analog phase shifters inserted before the antenna's radiating elements. By tuning the phase shifters phi, a number of constructive and destructive patterns are created. This deflects the resulting beam in the desired direction theta. The beam controlling phase shifts can be applied by analog phase shifters, as in this example here, or from the radio side as well. Let's have a deeper dive into this concept. The phase shift control can be fully digital by the baseband unit. In that case, we have a significant number of transceivers directly mapped to individual subarrays. This design gives us the best beamforming control, but of course on the expense of higher costs, power consumptions, and signaling overheads. We can also utilize a full analog beam control by introducing analog phase shifters. Here we have a single transceiver split among the radiating elements. This is, as expected, most cost efficient, but with least control. Eventually, the industry has also come up with a mix of both worlds as the hybrid beamformers. A reasonable number of transceivers with added analog phase shifters that are dynamically adjusted. There is a commonly held belief that a beamformer must involve active antennas or antennas with integrated radios inside. This is not always the case. Passive antennas, when used with 8T8R base station radios, can provide decent level of beam steering. The result is a beamformer that delivers cost-efficient coverage in low traffic and suburban areas. But how is it built? Let's find out together. The design usually consists of an external 8 transceivers radio connected to a passive beamforming antenna. With 8 transceivers, the beamformer can have 2D only horizontal beam steering capability. The resulting transformer is smaller and of less cost, but also practical and handy in many situations. An example of an 88R passive beamforming antenna can be seen on the left, built with 4 column arrays, each is dual polarized at plus and minus 45 degrees. Then the middle figure shows the simplified view of these 4 dual polarized columns. As the panel is two-dimensional, we can have vertical and horizontal phase control. The vertical beam direction is statically controlled by the traditional remote electrical downtilt settings, while the horizontal beam direction is dynamically digitally controlled in full by the radio itself. It is important to highlight that for beam steering to function, the involved arrays have to be on the same polarization. So moving to the right figure, we can think of the antenna built of 2 groups. Each group is of 4 similarly polarized subarrays. Then each subarray gets connected to a dedicated transceiver, ending up with 8 transceivers, hence the name 88R. Here the radius BBU applies phase and amplitude variations, and the beamformer is thus fully digital. The table shows an example of relative phase shifts and amplitudes that the radio needs to apply for each transmission mode and direction. While these settings can be accurately applied by the radio, there is no guarantee that the exact values will be received at the antenna's ports. This is especially true given the millimeter variances in the length of the connecting jumpers. The calibration port shown in top figure here is designed to compensate for any variance. In this approach, all subarrays are coupled to a single calibration port. For example, the calibration board shown in the middle figure utilizes Wilkinson power dividers that maintain a coupling level of minus 26 decibels between the RF input ports and the calibration ports. The 88R radio needs then to transmit a test signal on one antenna port at a time, which is then looped back to the radio over the calibration port for delay calculations. So what will be the maximum scanning angle for a beamformer? We have earlier seen how element spacing influences radiating patterns beam width. A similar concept applies to columns. A column's pattern horizontal beam width is inversely proportional to the intercolumn spacing, dx, as shown on the top left figure. Typically, 0.65 lambda spacing results in 65 degrees and half lambda spacing in 90 degrees horizontal beam width. On the other hand, the column spacing also decides on the maximum scanning angle before grating lobes or side lobes are generated. Typically, a half lambda results in the maximum span of plus or minus 90 degrees as shown in the bottom right chart in dotted orange line. In summary, even though a half lambda separation results in wider 90 degrees horizontal beam width, yet it has the best scanning range, and for that reason, most designs utilize this setting. A passive beamformer has 5 radiating patterns as can be seen on this slide. The column pattern is for an individual column before beam steering. It is used for uplink in some systems. The LTE broadcast pattern is an unsteerable wider beam that is usually used for downlink control channels. As the amplitude might be reduced or tapered on some ports for beamforming, a broadcast pattern could exhibit gain reduction, also known as weighting loss. Now, unlike LTE, 3GPP defined directional synchronization signals for 5G NR. This allows the G Node B BTS to sweep its broadcast signal in different directions using narrower and higher gain beams. The 5G NR broadcast pattern shown here captures the envelope for a 5G NR sweeping beam that can be used in planning tools. The service beam patterns are narrower, steerable beams that are mainly used for downlink data traffic. And finally, for the soft split case, the antenna phase and amplitude parameters are set to emulate a tweed beam antenna, that is like 3 antennas serving 6 sectors. The result shown on the bottom right is 2 service beams with fixed directions. Passive beamformers equipped with up to 8 radio transceivers are capable of dynamic horizontal digital beam steering, vertical analog electrical tilt, and 2x2 MIMO streams. So what happens if we increase the radio transceivers beyond 8, such as going for 32 and 64 transceivers? Well, let's find out here. Such a large number of transceivers results in what we call massive MIMO, allowing narrower, more focused, and highly directed beams. However, it is impractical to have 64 radios external to the antenna, and that is why we needed to develop active beamformers with embedded radios. Equipped with 32 or 64 transceivers, the beamformer can have meaningful 3D beam steering capabilities. This is of course an expensive, heavy, power-hungry, but also a super strong beamformer hero. To configure massive MIMO active beamformers, 3 factors must be considered: transceivers numbers, such as 32 or 64, beamforming type, like analog, digital, or hybrid, and the total antenna element numbers, as can be seen in the photo over here. Here is a quick reminder of our earlier discussed beamforming techniques. Active beamformers in millimeter waves are usually built over the hybrid beamformers platforms, while the sub-6 GHz solutions mostly utilize digital beamforming. To increase the panel gain, each active transceiver's RF chain can be split and mapped to more than one radiating antenna element. Let's assume a hypothetical 8 transceiver active beamformer maps to 4 subarrays as shown over here. Recall that the beamforming only works with similarly polarized elements. That is, the 8 transceivers will be divided into 4 co- and 4 cross-polarized subarrays, and each subarray mapped to one RF transceiver. The overall panel gain can be calculated by the shown formula over here. Expanding on that concept, the bottom figure shows an 88R passive beamformer compared to two 32T 32R active beamformer panels. The table lists different panel gain calculations for each polarization. The 88R on the first row has 4 horizontal subarrays, 1 vertical subarray, and 11 antenna elements per subarray, resulting in 21.48 dBi gain. The 32T32R case 1, which is shown on the third row, has 4 horizontal subarrays, 4 vertical subarrays, and 2 antenna elements per subarray, resulting in around 20.1 dBi gain. The 32T32R case 2, which is shown on the fifth row, has 8 horizontal subarrays, 2 vertical subarrays, and 6 antenna elements per subarray, resulting in around 24.85 dBi gain. We can thus conclude that a passive beamformer panel gain can exceed the active beamformer in some cases and under some configurations. But how are the beams themselves established inside the beamformer? As we all know, it is essential for the UE to establish a directional physical link connection with its initial access to the network. The 3GPP defines directional downlink synchronization signals for 5G new radio. which play an important role in beam management. Synchronization signals are sent over SS blocks, which in turn are embedded inside larger SS bursts. Each SS block in a burst is mapped to a certain angular direction. The number of beams is thus determined by the number of SS blocks inside an SS burst. By sequentially sweeping different angular directions, a G-node B covers a whole cell sector. The UE can then measure each SSB and identify the best SSB index for its current location. The 3GPP has also suggested three downlink management procedures, commonly known as P1, P2, and P3, for beam selection and refinement. These three procedures instruct the UE to enable certain transmission reception point (TRP) beam measurements and are meant to select the optimal beams as the UEs roam across the RAN. For instance, P1 triggers UE measurements of transmission beam selection. It typically uses wider or coarse beams in wider sweeping ranges. Then P2 triggers UE measurement for beam refinement. These are finer and narrower and possibly of narrower sweeping ranges, set of TRP TX beams than P1. On the other hand, P3 triggers measurements for UE receive beam change in cases of UE beamforming. Here the TRP transmit beam is fixed and the UE RX beam is being swept. 3GPP further specified that at least a network-triggered aperiodic beam reporting must be supported under P1, P2, and P3 related operations. Nevertheless, a UE can also trigger mechanisms to recover from beam failures. If you have been following up on recent updates, the Open RAN standards are now reaching advanced levels of maturity. For instance, the ORAN Alliance has recently published its 4 supported beamforming methods. The first method on the left uses a predefined set of beams known and stored inside the radio unit and can be selected by unique beam IDs. While the second method uses weight-based beamforming. Here, the RU receives the necessary pre-calculated weights, such as relative delays and amplitudes, to form the beam itself. Then in the third attribute-based case, the RU receives the beam description to form. This is, for example, includes the beam direction and width in vertical and horizontal directions. Finally, in the fourth method, the RU receives the channel estimates and scheduling information, which it then uses to calculate and then apply the necessary beamforming weights. In the current 5G new radio early stages, the predefined beams method seems to be adopted by many manufacturers. The ORAN has also released some implementation guidance as shown on this figure. There are two beam shapes defined such that energy in the downlink or sensitivity in the uplink is focused into either a coarse or fine granularity with possible overlaps. In this way, broadcast beams may be used to cover wider areas with less power or sensitivity, while higher power downlink beams or higher sensitivity uplink beams may be used per UE. This is very similar to the 3GPP procedures we have just seen. ORAN further recommends avoiding scheduling overlapping or neighboring beams simultaneously to avoid interference, of course. As we have seen, there are numerous beamformers heroes to choose from, such as the ones listed on the right of this chart, passive or active starting from 4 transceivers and above. We thus need to strike the correct balance between capabilities and cost for a better business case. The selection is basically based on 3 decision factors: the spectrum being used, the surrounding clutter and terrain, the cost, revenue, and ROI. Let's have a deeper look into these factors that can make or break a successful 5G investment strategy. The allocated spectrum resources have an impact on cell range, cell capacity, and the antenna's dimensions. So as you can imagine, spectrum has a strong influence when it comes to selecting the right beamformer. This chart explains the concept, showing the cell range on the horizontal x-axis and the bandwidth on the vertical y-axis. The sub 1 GHz low bands, shown as a green bar, have the best coverage reach, but like all other good things in life, is very scarce and valuable with very limited bandwidth and capacities. On the contrary, the millimeter waves high bands, shown as a red bar, have the widest bandwidth, but do lack good propagation characteristics and have the shortest cell range. Besides the wider bandwidth, there is also another big advantage in higher bands. You see, the radiating dipole sizes are functions of wavelength, and thus the higher bands allows us to pack more dipoles into smaller antenna sizes. Very suitable for dense urban areas where we need to hide our antennas from the public eyes. These two charts show a comparison between the 5G signal availability versus throughput from a test conducted in the US by OpenSignal. The chart on the top reflects 5G signal availability, time percentage, and the one below shows the 5G download speeds. In this comparison, Verizon millimeter wave 5G deployments show least availability, but also with best download speeds. This is because the millimeter waves have tremendous bandwidth, but with very limited coverage reach, as we all know by now. Now, what if we can get the merits of low band superb propagation with the high bands capacities? The figure on the top shows a typical macro site-to-site distance designed for low bands. Now, using higher bands such as 3.5 GHz for 5G capacities, our beamformers can boost the signal levels reach by focusing the radiated energy into narrower pencil-sharp beams. We also end up with better interference margins as beam 1 is not interfering user K in this example. So that solves our downlink problem to a big extent. But how about our uplink case? The UEs, as we all know, are mostly of limited power and computational resources that can't match the base station capabilities. The current uplink solutions rely on lower FDD bands for conveying the uplink signal. The bottom left figure shows the case of non-standalone 5G option 3X. Here the green LTE Node B is used for anchoring the blue 5G new radio signals towards a 4G core or the EPC. In such arrangement, we can reconfigure the uplink signal mapping from the new radio on high bands to LTE on middle bands for improving the uplink cell range. As we evolve into standalone modes, we lose this LTE anchoring advantage. But luckily, as can be seen on the bottom right figure, the dynamic spectrum sharing function, which as its name implies, allows sharing spectrum resources between more than one technology. That is particularly useful when 5G traffic is still at its infancy. In this example, a low-band FDD 700 MHz carrier is shared between LTE and 5G new radio, which in turn enables carrier aggregation with 3500 MHz for the supported devices. As of today, most of the 5G deployments and handset support is for the non-standalone architectures. So I thought to run a simple link budget analysis exercise and compare cell edge distances for different beamformers. For everyone's benefit, there is a useful free link budget tool that I've included a link for on this slide. The tool supports standard 3GPP path loss models to select from, like urban macro, rural macro, and urban micro. After adding and subtracting all gains and losses, the cell edge is where the received signals equal to the receiver sensitivity as shown on the chart here. This of course applies for downlink and uplink independently. In the following slides, we will calculate the link budget for an open rural environment. Let's start with the transmit powers. The table on the top lists our link budget entries, which we are going to fill up as we go on with this exercise. I have included on this slide a number of EIRP calculations for 8, 32, and 64 transceivers beamformers. The 88R passive beamformer EIRP is calculated per each polarization for 160 watt and 320 watt radius, while the active beamformers EIRP are extracted from datasheets. Comparing these downlink transmit powers, we can notice that a 320-watt passive beamformer can have a higher EIRP than a 32T32R active beamformer, but the 200-watt 64T64R shows the highest value for all in this example. Now, moving into the antenna panel gain, this can be easily calculated, as we have described before, using the number of radiating antenna elements and arrays. Sharp and directive beamformers beams are expected to reduce interference between nearby users. This effect is captured and quantified in the downlink interference margin entry, which can be obtained by computer simulations. I used some figures from an IEEE Vehicular Technology magazine paper that has its title listed on this slide. Interference margins tend to reduce by increasing the transceivers numbers. The receiver sensitivity is a function of bandwidth and signal-to-noise ratio, as shown on the formula over here. To obtain the signal-to-noise ratio, we need to map our target cell edge throughput to a modulation plus code rate combination. The table on the bottom over here shows an example of mapping modulation and code rate, or our target cell edge throughput, to a certain signal-to-noise ratio level. Such tables are unfortunately vendor specific and cannot be found in 3GPP standards. And finally, putting all these bits and pieces together, we get this bar chart shown over here. Downlink cell edges in blue bars for 8, 32, and 64 transceivers at 3500 MHz, and uplink cell edge in red bar for 1800 MHz. The 64T64R shows a much larger cell edge range driven by its higher EIRP and better interference margin, while the 8 and 32 transceivers beamformers experience a very comparable performance. However, the uplink red bar seems to be the limiting factor for all, and thus a massive 64 transceivers beamformer might not be our optimal choice in this example. We also have to note that these results are very much dependent on the target environment's assumptions. The cell edge distances will vary between dense urban to rural environments and with different target cell edge throughputs as well. While a heavily configured beamformer can support vertical and horizontal beamforming, not all terrains will benefit from this capability. Let's have a deeper look into the second beamformer selection factor effect, the surrounding terrain. For instance, the figure on the top describes a suburban environment with low height like 1 to 2 story houses. In this case, users are mainly horizontally distributed and will fall under one vertical main beam. Hence, vertical beam steering will not be adding much value. On the contrary, in the bottom figure, deployments in dense high-rise buildings terrains will need the vertical beam steering functionality to address users on different heights. I found a very interesting paper published on the IEEE Communications magazine that was addressing this exact argument. Here, a 64 transceivers radio mapped to 32 cross-polarized radiating elements with mostly horizontally spread users is assumed. On the top scenario, all 32 elements are placed horizontally, which means horizontal-only beam steering capability. The pattern plot on its right shows a very sharp steerable beam on the horizontal azimuth domain. The blue and red beams of users 1 and 2 respectively have minimal overlap chances and are thus highly decorrelated. Moving on to the middle scenario, our 32 elements are now placed in an 8 by 4 arrangement with half lambda separation in between. Because we reduce the horizontal elements from 32 to 8, we end up with thicker azimuth patterns, but still the user's patterns are not overlapping much and are decorrelated to a good extent. However, with only 4 vertical elements to steer the beam vertically, the vertical lobes are much wider and are very much overlapping. In the bottom scenario, the authors increased the vertical spacing from half lambda to 2 lambda. This reflects into sharper vertical beams, but on the expense of generating stronger side lobes. However, these now sharper vertical beams provided less overlapping and somewhat better patterns segregation. As most users were horizontally spread in this simulation, the paper shows highest spectral efficiency for the first scenario of sharp, horizontally only steerable beams. We can imagine that different results could have been obtained if the simulation had more vertically spread users, which exactly makes our point on how the terrain and users distribution heavily impacts our beamformer selection. As engineers, we always dream of the most sophisticated and technologically advanced equipment for our networks. But in the end, deployments have to be perfectly dimensioned for efficient TCOs and ROIs. It is impractical to hire a bus to drop only 2 passengers. Here, our third selection factor comes to play, the financials. It is estimated that only 10% of most networks cells are fully loaded. This is where the highest capacity solutions are needed and where the ROI can justify the more costly investments, such as choosing 64T64R beamformers, while perhaps 60 to 70% of the cells are underutilized and are always needed for coverage more than capacity. Here, a less capable, more cost-efficient, and less power-hungry beamformer can make a better fit. Another study by Ericsson on the bottom figure showed that massive beamformers' effect on capacity is mainly visible at shorter side-to-side distances. For example, in a dense area with around 200-meter inter-side distance, the light blue bars, a 64 transceiver beamformer increased capacity to 10x from an equivalent 16T16R beamformer. On the other hand, for a 1 kilometer inter-side distances, the dark blue bars, there was almost no capacity gain going on from more than 16 transceiver beamformers. Hence, the extra investment cannot be justified. When it comes to longer inter-site distances, transmitted powers are crucial to decrease the overall number of sites needed for coverage purposes. On this slide, I'm comparing the same 4-column passive beamforming antenna hooked to an 8-transceiver beamforming radio on the left and to two 4-transceivers 4x4 MIMO radios on the right. The 8-transceiver beamformer will have a higher transmit power as 4 transceivers will be combined to form one beam, in contrast to independent streams for the non-beamforming case. The 88R case will also have a narrower steerable beam, resulting in higher gain by almost 5.5 decibels. Now let's compare the case of passive 8 transceivers beamformer with 88 antenna elements on the left to an active 32 transceivers beamformer with 64 antenna elements on the right. As both have 4 horizontal antenna elements, we expect to have similar azimuth beam width. Now, the active beamformer will have vertical and horizontal beam steering capabilities. However, as the passive solution has 11 vertical elements compared to 8 for the active, the vertical beam width will be sharper in the passive beamformer's case, resulting in higher panel gain and probably wider coverage. So again, the selection is highly dependent on the capacity vs coverage needs. In summary, the expected traffic and revenue provide a third dimension in choosing our beamformer configuration. In low revenue, flatter terrains, a 2D passive beamformer might be a better choice for a comparable performance to an active beamformer in this environment, but with much less cost and power consumptions. As we span the chart to the right into the higher traffic areas and more complex terrains, a stronger 3D active beamformer appears to be a better choice with fast ROI. To take this from theory into reality, we have worked with operators and RAN vendors to benchmark an active 64T64R to a passive 88R beamformer. The area under test is a suburb of low-height villas and low traffic. The two sectors on the map were swapped between both configurations under similar conditions. The slide here compares the received power levels of the synchronization signals for both beamformers configured with 4 and 8 SSB beams. If we compare the theoretical ARP, we can see around 1.5 dB higher transmit levels in the 64T64R case. To make it easier to compare, let's focus on the street surrounded by the oval shape. First observation is that increasing the number of beams from 4 to 8 did not enhance the 88R signal level performance, while it has done that for the 64T64R case, to some extent. Second observation from the CDF plots on the right, the 1.5 dB advantage of the 64T64R beamformer reflects more on the 8 SSB case. This result re-emphasizes the marginal difference between both beamformers in flat terrain environment, like what we have seen here. Now it's time to discuss some innovations that can make our 5G deployments easier. Let's start by the Open RAN concept. Traditionally, as shown on the left figure, a typical mobile site consists of a baseband unit, a remote radio unit, and a passive antenna. This architecture has proprietary vendor-specific BBU RRU interface, such as the CIPRI on this figure, and does not allow for efficient centralized functions. With the integration of radios and antennas into a single beamformer unit, many operators are pushing to open the beamformer's interface, such as the Open Front Haul interface, with a new centralized and virtualized architecture as shown on this figure. The Open RAN approach has also gained political momentum by countries that do not own 5G RAN vendors and have security concerns. With an Open RAN approach, software companies can easily enter the market with virtualized RAN solutions. But in the end, this is to free the beamformers from specific vendors' lockdown and encourages innovation in the industry by smaller startups and new players. For loaded towers and structures, new approaches are needed to facilitate the 5G deployments. This design over here shows a passive beamformer with its radio integrated on the antenna's back panel. No additional mounting space is needed, and that's why we call it zero footprint. The antenna itself is also a mix between 5G passive beamformer and traditional 3G and 4G ports shown in the bottom with surrounding yellow and red circles. Also notice this new cluster connector. These typically combine 9 RF cables into only 2 sockets. Now, adding an active beamformer to existing sites can be challenging for zoning restrictions or exceeding towers' windowed capacities. A new approach is to build modular active beamformer units on top of legacy 3G, 4G antennas. These units have parts of the legacy antenna passing through them. In that way, the passive antenna can still maintain its full array length and high gain, while the active beamformer is embedded inside the legacy antenna's form factor. I always like to end the beamformers comparison session with this question. If we confront a passive and an active beamformer in a battlefield, who do you think will win the race? So, well, both have equal chances depending on the battlefield environment itself, the spectrum being used, the surrounding terrain, and the generated traffic. But in the end, beamformers are essential tools that are here for us to save our 5G deployments. We just need to wisely choose the right one. So many thanks for joining our session today. Hope it has been useful, and don't forget to download our white paper for more details. Hope to see you all again soon in upcoming webinars. Now let's take some questions before we close, and back to you, Vivian.
Thanks, Dr. Mohammed. Before we move to Q&A, please allow me to show you the latest 5G resources from us. As mentioned by Dr. Mohammed, you may want to check out our new white paper on Beamformers Explained, written by Dr. Mohammed himself. As you know, we will be sharing this presentation file with you, so you could click on the links to check out the white paper and the rest of the resources at your convenience.